Last section we discussed functions and their domains, and we were able to get an idea of what a function is doing by looking at its graph. But sometimes it turns out that the most interesting stuff occurs at points that are not even in the domain of the function. Let's look at two possibilities. Let's look at two functions. Say f of x is x squared minus 1 divided by x minus 1. And we'll also look at the function g of x, which is x squared minus 2 divided by x minus 1. Let's go ahead and graph these. But before we do so, notice that both of these are fractions, and so we can actually find the domains by seeing where the denominator is equal to 0. Hopefully it's pretty easy to see that it only happens when x is equal to 1, so the domain of both of these functions is everything except for 1. Let's go ahead and write that way. If I go ahead and graph those, let's go ahead and start with f. F of x is x squared minus 1 divided by x minus 1. That actually looks like a line. Whether or not it actually is one, we'd have to actually check. Notice that it does show something at 1, though technically we have to exclude that because if we try to plug 1 into the formula, things will break. If we plot the other one, we have x squared minus 2, which we're dividing by x minus 1. This time, it definitely does not look like a line. And if we look at what's happening at 1, just let x equals 1, that's this vertical line. It's showing everything around that vertical line is what's happening to these functions around x equals 1. Our f function just looks like it just goes right through. Our g function, on the other hand, looks like it shoots off to very positive numbers when we're coming in from the left, but then it somehow jumps down here and starts coming up from below on the right. These functions look very similar in their formulas, and when we're very far away from x equals 1, they actually look very similar as well. They get really close over here and over here. But when we're close to 1, their behavior is very different from each other. What we're going to look at today is a way of describing this behavior, especially around points that are not in the domain of our functions, and even some where we are going to be looking at points in their domains. We are going to describe this through the concept of a limit. The limit of a function, say function f, at a point x equals c is L. This is written in the format lim with the x going to c below it, then f of x equals L. That's the notation we have for this. If when x is close to, put that in quotation marks. This is not a formal definition. The formal definition for what a limit is actually is a fairly complicated thing. The book, I don't think, ever talks about it. It doesn't talk about it now, at least. I don't know if it ever comes back to the idea, but I doubt it. If you want a more formal definition, you might want to look up something like Epsilon delta definition. But we'll not get into that here because it's not really too useful for what we're going to be doing with it. But what this means is that when x is close to c, then f of x is close to L. And when I say close to, especially with the x is close to c, we're not actually talking about when x equals c. We're actually looking at just the points that are close to whatever that c value is. On the other hand, when talking about the f of x values, Whether or not they equal L or not is just up to the function. But let's look at an example of this. We want to look at the limit as x goes to 5 of x squared. Our function here is x squared, our c is 5, and we want to see, is there an L that this is equal to? Is there a limit to this function as x goes to 5? Basically, if we let the x values get close to 5, what is the x squared values close to? The easiest way to tackle this is look at a table. We'll make a table of different x values, specifically ones that are close to 5. In fact, I'm going to kind of say this will be represent 5, and I'll put numbers that are below 5 above it and above 5 below it. So might start with something like 4. If I put 4 into our function, say this is f of x, 4 squared, of course, is 16. If we get a little bit closer, maybe we'll go to 4.5. That's closer to 5 than we were before. We get something like 20.25. Maybe we'll jump to 4.9. 4.9 squared is 24.01. Let's do a couple more. 4.99. When I square that, I get 24.9001. And even closer, 4.999. When I square that, of course I'm using a calculator for all of this. I'm not doing this all in my head. But I get 24.990001. And hopefully at this point we can kind of see that as we get closer and closer to 5, our numbers are getting closer and closer to something. You might be able to guess what that is, but let's look at the other direction first before we talk about that. So I started 1 away from 5. I'll start 1 away from 5 on the other side. Go to 6. If I square 6, I get 36. If I get a little bit closer, let's go to 5.5. Square that is 30.25. If I get a little bit closer, we'll go down to 5.1. The square of 5.1 is 26.01. A little bit closer still, maybe go with 5.01. The square of that is 25.1001. Finally, let's stop with 5.001. When I square that, I get 25.100, or wait, reading the wrong line there. 010001. Now note that 5 is in the domain of x squared. That we didn't have a problem with domain here. And nothing about the definition of limit requires us to only be looking at points that are not in the domain. Since 5 is in the domain of x squared, we can go ahead and plug in 5. Of course, 5 squared is 25. We already knew that. But when we're talking about limits, we're actually kind of ignoring this fact. We're ignoring the fact that we already know what this value is. We're ignoring that. It's just not in the realm of what we're even talking about. But the very fact that we looked at numbers that were close to 5, when we do look at what numbers these values of our function are getting close to, it shouldn't be too surprising that it is actually 25. That the limit here, as x goes to 5, of x squared is just 25. This happens a lot when we do have a function that is defined for the value here. A lot of times it does turn out that we can go ahead and plug in that number into our function and see what we get. Not always, and that's why we have to be a little bit careful about it. But we'll discuss in more detail when that can be done in the next section. Now let's look at an example of a function where we are approaching a number that's not in the domain. We'll take the function from our first example. Remember there, f of x was x squared minus 1 over x minus 1, or at least we're using one of the functions from there. We might discuss the g that we had from that one a little bit later. But we're going to take the limit of this function as x goes to 1. What happens to this function? We'll go ahead and make a table, like we did in the last one. Again, I'm going to go ahead and put a dash line here. This will represent when x equals 1. Of course, we can't plug it in here at all, so we don't know. Well, shouldn't say we don't know. There just isn't a value of this function at 1 to be able to talk about. But we can go ahead and pick values that are close to 1. We'll go ahead and start with 0 and 2. Those were 1 away from 1. If I plug in 0 into this function, we'll have to do a little bit more work than just squaring it like we did before. But it shouldn't be too hard to see that we just get negative 1 over negative 1, and we get 1. For 2, we have 4 minus 1, so we get a 3 on top, but we get a 1 on the bottom. So we end up with a 3. If we get closer, and I just use a calculator for this, so I went ahead and took 0.9, 0.99, 0.999, and 0.9999. And on the other side, I took 1.1, 1.01, 1.001, and 1.0001. And I've just plugged those into a calculator using this formula right here. For 0.9, got 1.9. For 0.99, I get 1.99, then 1.999, and then 1.9999. On the other side, 1.1 became a 2.1, 1.01 became a 2.01, then 2.001, and 2.0001. And so even though we don't know or don't have a value for when x equals 1, it just doesn't exist, it's actually pretty clear once we start plugging in values here that it's getting really close to 2. And so the limit of this function at 1 is equal to 2. In some ways, for this particular example, we might say that, well, the function itself is not defined at 1, but if we were to kind of just give it a definition at 1 to make it work out nicely, that definition should be 2. Basically, if we were to plot this one, and I guess we still have this, if I take out the g there, we can kind of see here that, well, it is a line. This line here is representing our function. It should have an open circle at 1 because it's not technically defined there. But I can essentially fill in that hole by putting in 2 when x equals 1. That's just what we should have plugged the hole with in the first place. It's just the fact that we don't have 1 in the domain is just a fact from the fact that our formula doesn't work there. But maybe we should repair that function in some way. Now, not every limit is like that, but a lot of times that's kind of the idea that we want to have behind it. If it does have a limit at a point not in its domain, that's what numbers should have been there all along. Now, if we had to make a table like we did in the last two examples every time we talk about limits, it'd get really tedious. And it really wouldn't be very helpful, because it'd just take too long for every single problem that we'd have to do. But the advantage of limits is that we can actually derive a number of rules that make finding limits of functions a lot easier to do. The first thing we can note is that, like in our x squared example, most limits, when we're taking the limits to a point in the domain of our function, turn out to be just the same thing as the value of the function themselves. So we can say that frequently the limit as x goes to c of f of x is this f of c. And in fact, for a lot of examples that we will come across, the first thing I will try to do when taking the limit is see if I can plug in that value. If I can plug in that c, that is a very good possibility for what the answer should be. We'll give more details about when that is true and when that's not in the next section. But this is definitely true for most of our basic functions. Specifically, something like the limit as x goes to c of b. B here is just a constant. So it's like taking what is the limit as x goes to 4 of 2. Well, 2 never changes. If I let the x's get close to some number, I'm still just getting 2's out every time. So if we're dealing with a constant function, then we just still get that constant out, even though we're letting the x value that's not even being used move around. Next easiest example, well, what does x approach, or what was x approach as x approaches c? Well, hopefully that is pretty obviously c. If we let x go to c, then x is going to c. Sounds like a tautology, actually. What if we have x to a positive integer power? This would be like, well, I guess technically here, x to the 1 power we've already even taken care of. We could have x squared, x cubed, x to the 4th, all of those. If we let x go to c for any of those powers of x, then all we get is the power of c. So this goes back to our x squared example. When we were taking the limit of x squared as x goes to 5, we just got 5 squared. Finally, for our basic building block problems, we're going to look at nth roots. So these are kind of still powers of x. Remember, the nth root of x is really x to the 1 over n power. Though I was saying here that we're only looking at positive integers, it actually works out a little bit more generally than that. But for right now, we're also essentially adding in the fractional powers. Well, it shouldn't be too surprising that this is also an example where we can just plug in our number. We get the nth root of c. Though we do have to be a little bit careful here. If n is even, then c has to be positive. Because obviously we can't take the limit of the square root of x as x goes to -1. Because, well, the square root of -1 is not a real number that we can work with. And there's not even, say, numbers around -1 to be able to plug into the square root function in the first place. At least not without getting into complex numbers, which we don't want to do here. But essentially, 3 and 4 here are kind of saying that, well, we can work with different powers of x. Except we might just have to worry about some conditions to make sure that we don't plug negatives under a square root or something like that. Technically here we could also say in 3 that we could use negative powers. Remember, x to the negative n is 1 over x to the n. Of course, in that case, we do need to make sure that c is not 0. Obviously, the limit as x goes to c of 1 over x, or as the limit as x goes to 0 of 1 over x doesn't work, because we can't plug in 0 into 1 over x. But basically, we're just saying here that all of our powers of x work kind of the way you would expect them to work. As long as it makes sense to plug in c into those powers, then the limit of that power will also be the value of that power at c. Those are our building blocks. We can combine them all to make more complicated limits. So we have a theorem here. Properties of limits. Here we're going to assume that we already have some limits of some functions. The limit as x goes to c of f of x we're going to say is L. And the limit as x goes to c of g of x is k. So if we already know the limits of two functions at c, then we can combine those two functions into more functions. We looked at this when we talked about functions last time. There are various ways of putting two functions together. Our first one, well, here we're actually only even going to work with f, but what if we take f and we multiply it by a number? So let's say maybe we know how to work with x squared so far. What if we had 2x squared? Could we look at limits of that one? Well, what does a 2 actually do? Well, it just multiplies the result of our limit. So if we took 2x squared and we took the limit as x goes to 5, well, the x squared is going to go to 25, and so 2x squared is going to go to 2 times 25, or 50. If we take the sum of those two functions, well, this part's going to L, this part's going to K, so the whole thing turns out to just go to L plus K. This works with subtraction as well. If I'm subtracting them instead, I subtract L and K. If I multiply, take f of x times g of x, we just go to L times K. So kind of what we would expect to have happen. This part's going to L, this part's going to K. The fact that these are going to L and K separately doesn't really change anything. They're still going to L and K separately, and then they get multiplied. So it doesn't matter if we do the multiplication here or we do it afterwards. We also talked about division. If I divide f of x and g of x, then we're going to just go to the quotient, L over K. As long as K here is not 0. If K does equal 0, we can't use that. And that's actually one of the places where we end up running into a lot, where we actually have to step back and maybe do something different. Maybe this won't work out. But as long as K is not 0, even if L is 0, as long as K is not 0, then we can just go ahead and do it this way. There's no problem. Our last two properties are actually very similar to what we had the last two of on the previous page. If I take f of x to the nth power or to the nth root, well, this time we're not just taking x to the n and getting c to the n. Here we're taking f of x to the n, and we're going to get L to the n. And same thing here. The nth root of f of x goes to the nth root of L. Of course, here, keep in mind that we need to not be putting anything negative under a square root. So if n is even, we have to have L is bigger than 0. L has to be positive. But all of this means that if we take something like a polynomial, so let's go ahead and just pick a random polynomial. P of x is equal to x cubed plus 7x squared. Actually, to make that work out nicer, let's go ahead and make that minus 7x squared plus 2x minus 4. I want to take the limit of p of x as x goes to 1. Yeah, let's actually make it like x goes to 2. We want to find the limit of this polynomial as x goes to 2. And it's pretty simple. So p of x is just this thing, but this is just a sum and difference of different things. When I have a sum of things, I can split it up into a limit of the first piece plus a limit of the second piece. Because I could essentially just write down here, limit as x goes to c of f of x, and limit as x goes to c of g of x. So I can go ahead and write this as the limit as x goes to 2 of x cubed minus the limit as x goes to 2 of 7x squared plus the limit as x goes to 2 of 2x and minus the limit as x goes to 2 of 4. In fact, I could go ahead and pull out my 7 and my 2. The limit as x goes to 2 of x cubed minus 7 times the limit as x goes to 2 of x squared plus 2 times the limit as x goes to 2 of x minus the limit as x goes to 2 of 4. And that just comes from my first property here. If I have a constant times my function, I can pull out that constant before I look at the limit of the function. This L is just the limit as x goes to c of f of x. And now I'm just working with powers of x. The limit as x goes to 2 of x cubed is 2 cubed. Then we have 7 times the limit as x goes to 2 of x squared is 2 squared. The limit as x goes to 2 of x is just 2. And then the limit of a constant, this 4 doesn't change, so it stays 4. So we have 8 minus 28 plus 4 minus 4. Of course, the 4's cancel out. 8 minus 28 gives us a negative 20. And which, of course, is just what we would have got if we plugged 2 into the polynomial in the first place. That's essentially what we ended up doing. This line right here is literally just p of 2. That's what we get when we plug 2 into this formula. And that's just going to happen every time we work with polynomials. That's a theorem that we can always use. If p is a polynomial, then the limit for any c of p of x is equal to p of c. This is a nice property of polynomials that we're going to talk about again in the next section. This is a property called continuity. The saying that any polynomial is a continuous function. But we'll get into what that means in the next section. Now, we can't always do this. We can't just always plug in the value. I mean, we already saw that with our function that, yeah, this one right here, where we could not plug in 1. That means these properties aren't going to work immediately, and we're going to have to do a little bit more work to do that. I'm going to go ahead and do that in another video coming up. Well, it'll be posted at the same time as this one, but I want to split that up so we don't have just one big, long video. So meet me there, and we'll get into how we would handle various other functions, and what are the other possibilities for how limits might work. So I'll see you there.